My talk will be focused on a few aspects of precision physics, mainly those aspects which are dealing with muons and with a kind of focus on ongoing and plan to go soon experiments in the field of muon physics. So I will start with a brief introduction, and we will first take a look at the anomalous magnetic moment of the muon and relevant experiments and relevant theoretical advances in the field of anomalous magnetic moment of the muon. Then we will discuss the conversion decay of the muon with lepton flavor, with lepton number violation, and we will briefly talk about muon decays in a bound state of when muon is captured on an orbit of a nucleus. So why do we care about all these things? First of all, this is very interesting because these kind of topics require extreme precision, and in the last years, this extreme precision had become really achievable both by experimentalists and also by theory. So this is a place where extreme precision in theory can meet extreme precision in experiment. And this is very interesting because usually people think of modern particle physics as a high energy frontier. So due to LHC success and so on. So when really the energy is high, when the machine is very big, and when it is very expensive to convey the experiment. So this is kind of opposite situation where we really can touch the physics beyond standard model, do some really interesting research in particle physics, not really needing the high energy at all. So the focus shifts to high intensity, not the high energy. So, and mainly the experiments which drive us into this field are the new experiments at Fermilab, namely Mu2E experiment and Mu G-2 experiment. And also there is activity in Japan at JPARC, which is called COMET, on a very similar scientific background. So let me start with the anomalous magnetic moment of the muon. And so as a brief reminder, so where we start, so the particles with spin can have intrinsic magnetic moment, and we really can feel that the particle has this intrinsic magnetic moment as this particle really deflects when it moves in homogeneous magnetic field. So if you construct a Hamiltonian of such a particle, this would be minus mu, where mu is the magnetic moment times the external magnetic field. So, but if we look a bit deeper, so the magnetic moment is connected to the spin operator of the particle via a so-called G factor. So G mu or simply G in the course of this talk. So this G factor equals to 2 plus 2 a mu, and this small fraction a mu is due to quantum correction. So this is called anomalous magnetic moment. And people usually say anomalous magnetic moment, but write down G-2. So this is a kind of slang in these activities. And I also will, in a few cases, say G-2, in a few cases anomalous magnetic moment. This is actually the same thing connected by a very simple formula. The amazing story about a mu is that it is measured to an extremely high precision, 0.5 parse per mu. So this is one of the best known objects in the world, despite the fact that this is a tiny correction to a thing which is the anomalous magnetic moment of a particle which we typically have in a collider or in some experimental setup. So this is actually the way how people were able to measure the anomalous magnetic moment of the muon. So in the beginning, this picture is taken from the web page of Brookhaven National Laboratory, where the G-2 experiment took place. So they have the proton beam, and then they hit this proton beam on a target, and that produce pions. And these pions, as they fly away from the target, they decay into muons. So this is the main decay mode for pions. And then these muons, this gives us a source of muons. So then these muons get captured in a storage ring. So, and then, of course, the question is, how can we build a storage ring for muons? Because muons are not stable particles. So typically we have storage rings for protons, or antiprotons, or electrons, positrons, which are stable, but muons are not stable. So how do we do that? So and here is kind of a key to that. So muon, if we boost the muons, they can live long enough for the purposes of our measurement. So, and in particular for this experiment, they are boosted with a gamma factor of 29.3. And this is not just an arbitrary number. This is a very specific number. And actually using gamma factor equals to 29.3 allows us to make this measurement, really. So, and this is so-called magic gamma number. So in the next slide, we will take a look why it is so. So, and the experimental setup is the following. So we want to focus this muon beam inside the storage ring with electric quadruples. And then we put the storage ring in a homogeneous magnetic field. So we need a huge magnet of very high quality. And we observe the precession of the spin of the muon as it travels inside the storage ring. So actually in the experiment, they count the events which are directly related to the precession frequency. So, and this is the full formula for the precession frequency for a spin in external magnetic and electric field. So actually we need the electric field in order to focus the beam. So and magic gamma factor, which equals to 29.3, allows us to eliminate the dependency on the electric field, which is absolutely crucial in order for us in order to be able to convey this experiment. So we can use the electric quadruples for focusing, and then actually the precession frequency is directly proportional to the tiny thing which we measure, a mu. So the statistics on observed events is directly related to the statistical error for a mu. So that's how it is possible to achieve that high precision in measurement of a mu. So of course, this formula is known for many years, and the idea to choose this magic gamma is not a new idea. So, but the technological developments in our century allowed really to build the magnet of that quality in order to convey this experiment, and also to have a good source of high energy protons. So if we speak about the anomalous magnetic moment of the particle on a level of quantum field theory, so what we actually have is the vertex correction. So in the vertex where photon interacts with the lepton, we have two so-called form factors, electric and magnetic form factors, so-called Dirac and Pauli form factors. And if Q squared, if the form momentum transfer squared equals to 0, this electric form factor goes to unity, and the magnetic form factor at 0 is a mu. This is what we measure. So as we have this picture in a so-called quantum field theoretical view, this gives us an instruction how can we, in quantum field theory, really do the calculation of a mu. So since we have some kind of quantum corrections which enter this vertex, we can do the calculations with those quantum corrections, and then we get our theoretical precision of a mu, prediction for a mu, which we can compare with experimental results. So these are typical examples of corrections which are really hard to evaluate in theory. So these are related to the hadronic contribution. So you see, so roughly we can separate different types of contributions to mu. So the one from quantum molecular dynamics, electroweak corrections, also the Higgs boson it has its influence on the value of a mu, but it is tiny. So what really worries people in this field is the hadronic contributions. And the better we know the hadronic contributions, the more we can tell about new physics contributions to this stuff. So actually, our discovery power for physics beyond the standard model in the a new field is limited by the theoretical accuracy with which we can calculate the hadronic contributions to the anomalous magnetic mode. So there are two types of this, and this one can be related to the so-called R function, which can be measured experimentally on, say, E plus E minus colliders when electron and positron annihilates into some hadronic final state. So then we measure the cross section, so-called hadronic cross section. So, but this guy cannot be really measured experimentally, and there are only model-dependent bridges to what we actually know about the properties of hadron. So I speak a lot about these guys because this is probably the closest point to my field of research within the scope of this talk. So this is how the magnet looks like. So it is roughly 14 meters in the diameter, so this is not a huge experimental setup, though it is quite big. And actually, as the Brookhaven experiment finished and published their result, people found out that there is a tension between theory and experiment, which was reported at the level 3.5 sigma in 2012. And later on, this number even grew a bit higher. So as far as I know, there is still a tension between experimental and theoretical values for a mu. The tension is still low to claim this discovery of new physics or whatever. So this is rather a guide for us to take a better look on what's going on there to improve the precision. So on the theory side, we wanted to improve the precision of hadronic contributions, but on the experimental side, a new experiment was proposed to measure a mu with better precision. So this is a new experiment at Fermilab. So as you see in this picture, this magnet arrives to Fermilab. So it is quite big, but it was possible to put it on a track to move there. So actually, the magnet was reused. So this is the same magnet which was used previously in Brookhaven, and they had to move it quite a long way to get to Chicago. So this is the real view of the Muon campus in Fermilab. So actually, as far as I know, the groundworks are finished by now, and they are actually trying to run beams and to do some sorts of experiment, for example, to cool down the magnet. And I know that last year, at the end of last year, they successfully cooled down the magnet, and they really had this nice and high quality homogeneous magnetic field there. So this is a place where G-2 experiment is situated. And here is another Muon experiment in Fermilab, Mu2E. So now we will move on to the next experiment about Muon decay. So if you have questions so far, please stop me. Yeah. So now we switch to Muon decays. So if you want to take home one thing from this lecture, is this this paper. So take a look at this paper, at this article in the Symmetry magazine, to get an idea how the Muon guys hunt for new physics in Fermilab. So this is quite old paper, so article, but it is still really worth reading. So take a look. It's not complicated. So it is written for a wide audience. So try to read it, and you will know a lot about what's going on with muons these days. So let me remind one basic thing. So if you have a free muon in the standard model, it decays to electron and neutrino, antineutrino. So you have muon neutrino and electron antineutrino. And there are, of course, some kind of radiative corrections to this decay, but this is what is called Michel decay. And Michel decay is known since 1950, I guess, and there is a formula for Michel decay. So this is a formula which gives us the Fermi constant, right? So the Fermi constant is one of the quantities in practical data booklet in the standard model, which is measured to very high precision. So this is a very well known quantity. So actually the formula is known for years. The radiative corrections are known for years, but there is still ongoing work in the calculations, in the improvements of radiative corrections. And this is how the differential distribution looks like. So for us, it will be important if you remember the shape. So you see, the spectrum has a very tough cut on the high energy side. So there are actually no events over there, and this is because we are looking at this decay now, excluding the radiative corrections and excluding possible emission of, say, final state photons or this kind of corrections. So, and yes, it was first, the shape was calculated by Michel in 1950. So, and this is the shape which is still in use. So, how do people use Michel decay for precision measurements? So, if you measure the mean lifetime of muon, and it is possible to measure the mean lifetime of muon with a very high precision because of for example, the Milan experiment in Paul Scherrer Institute. So they had a great amount of muons. So they had very good statistics there, and they measured the lifetime with a high precision, and then using the formula, the Michel decay formula, you directly get G mu, also with a very high precision. But on the theory side, you can do the calculation, say, vice versa. So you can really do this electroweak stuff there, and then you express the Fermi constant in terms of alpha, the electroweak alpha times phi, and here we have the mass of W boson entering the formula and mass of Z boson, and then we have some radiative corrections which are also kind of under development now, but already known to quite high precision. So, and this allows us to give a purely theoretical estimate for the Fermi constant, which is with a very high precision. So this is one more place where theory and experiment really meet each other at the level of very high precision. Okay, so now we move on to a bit more complicated things. So what if a muon could decay into electron and photon? So these are so-called charged lepton flavor violation decays. So what we know about charged lepton flavor violation decays is that they have never been observed so far. So if I'm wrong at this point, please let me know. But according to my knowledge, they have never been observed so far. And these are the processes which are very promising for the search of physics beyond the standard model. Because in the standard model we have, say, 0, it is say, much easier to find some bump on top of zero rather than looking for a bump on top of something. So the recent experimental limits on charge leptons level violating decays are summarized in this paper. So and here are the limits on the branching ratios for these decays. So you can get a feeling of what is the level of precision in this field. So this is at level 10 to minus 13. Okay, so how do we feel this branching ratio? So Taras had written a formula here on the whiteboard. So the branching ratio, so this is actually the probability of a muon to decay into this stuff. So, and the probability is very low. So here is a summary table of the progress in this field. So, on this axis we have years, so the date. So this is the place where we are now, and here is the Mu2E and COMET. So these are the planned accuracy for this kind of measurements. And we expect that Project X will even do better for experiment. So this is the point which is already available, so with the MAG experiment. So you see, here is the logarithmic scale, so the progress in this field is quite impressive. Okay. So I've told you that this kind of decay of muon into electron and photon is forbidden in standard model. So and in standard model, this is the probability is simply zero. And the only option to have a non-zero probability is to extend the standard model with some kind of physics, new physics. So one of the types of new physics which we believe is not new physics really is the neutrino mixing. So if we allow neutrino mixing, then this kind of process really can take place. This is strictly speaking not a standard model process, but this is very close to standard model as this kind of is. But this process takes place at the one loop level, and the probability is still extremely small. So even in this extension of standard model, which we believe is the nature, the probability is very small. So there is absolutely no hope to measure this kind of quantity. So technically speaking, this is still kind of zero. So and people want to find some signals of new physics on top of that kind of zero. Okay, so here is an example of the type of new physics people are trying to look for in this kind of decays. So one of the ways to parameterize this new physics is to introduce the lambda parameter, which plays as a mass scale, and kappa, which plays as a coupling, and people write down some kind of effective Lagrangian for this kind of new physics contributions. And then one can, using this vocabulary, one can put different kind of beyond the standard model theories onto a same table and compare them, compare their predictions for this kind of processes, and also one can make this kind of fancy plots, so kind of exclusion plots in terms of kappa, our effective coupling parameter, and lambda, our effective mass scale. So the shaded areas are what is actually excluded by experiment. And then here are the lines which somehow reflect the expected exclusion level for the new experiments, like COMET and U2E in Fermilab. Okay, so now we go to even more complicated things. So how can we look for physics beyond the standard model in muon decays in practice? So in practice, we need these muons to be captured on the orbits of say, aluminum. So a lot of experiments have aluminum target, and they put the muon beam on the target, and then they produce the atoms where one of the electrons on the orbit is replaced by a muon. So this is what the experimental setup starts with. So you have an aluminum atom where one of the electrons is replaced by a muon. And then, due to the fact that muon is not stable, this muon decays. And we are looking for those kinds of muon decay where only electron is emitted in the final state. So, and then the photon is what is exchanged between the decaying muon and the nucleus. Apparently, in the last years, there was a very good experimental technique developed, which allows us to produce a huge number of muonic atoms. So this is a sketch of what's the idea behind that. So you have the proton being in the beginning, and then these protons hit on the target, and then you have pions, and these pions decay into muons, and then these muons are guided to a target, say aluminum target, where the muonic aluminum is produced. So the signal is this stuff. So the conversion of muon into electron. So we have exactly the same nucleus in the beginnings, in the initial state, and in the final state. So by that we exclude so-called internal transitions where muon is captured by the nucleus itself, and the proton gets converted to neutron. But so that stuff is so complicated, but that is the background for this search. So we are really looking for muons decaying in orbit. So the slang in this field is DIO, decay in orbit. So they're looking for muon decays in orbit. And this is a kind of sketch how this process takes place. So this is the standard model. So this is the main decay mode for muon. So this is the same stuff with the photon exchange. So and this standard model stuff is a background for us. And since we have a recoil effect, now the Michel spectrum gets a bit, say, shifted, tilted. So we will see in a moment how it looks like. Great. So here is how the Michel spectrum looks like. So remember, there was a very sharp cut on the Michel spectrum when the muon is free. So now, if the muon is decaying in orbit, then this sharp cut gets mirrored, and also due to radiative corrections, the tail gets some contribution, some enhancement. So this is not zero. This is something like this. So the picture on the right-hand side is the zoom of the tail of the distribution. And actually, the tail is the place where people are looking for this physics beyond the standard model. So they're looking for a kind of a sharp peak signal here on top of this tail. So that would be an indication of newly found charged-lepton flavor-violating decay of muon in orbit. And since the probability of this event is low, we need to have a theoretical precision and Monte Carlo estimation for this tail also at a quite high level of our confidence of what's going on in the tail. And during the last years, there was a very interesting activity in the field of radiative correction calculations, which allowed to really find the true shape of this tail. Okay, so though the Michel decay spectrum is known since 1950, and it is present in many textbooks now, So there is still an ongoing activity in this field, and there is still a place for new ideas, for new improvements, and the importance of radiative corrections in the process of muon decay in orbit is very high. It is really a requirement from the experimentalist side for theorists to do the calculations more precisely, to include the sublinear corrections in a consistent way. So, and there is still a new activity in the really QED calculations, so not really electroweak, but even at the level of QED, there is still a room for new calculations, so which are needed at this point. So this is how the Mu2E experiment kind of looks like, and the aim of this experiment is to get to an exclusion limit of 10 to minus 70. So this is the intensity frontier, the precision frontier, and in a few years, couple years, they will start this measurement. And actually, Japanese are kind of faster with that. So the COMET experiment is expected to start this year, and I hope they will really start. And they have a similar aim on the precision. So if you are interested in the experimental setups, please look at the web pages and look into the references which are in the slides. Great. So here is a kind of summary. I tried to argue that there is a lot of exciting physics around muons. And this is kind of modern and really very much appreciated physics, which is kind of in a contrast to what people usually consider when they hear particle physics. So particle physics is not only LHC. Modern particle physics is not only high energy. So even at low energies, if you get very high intensity beams, if you have very advanced theoretical calculations, you can actually touch the same questions which people try to address with high energy machines. So this is a place where these two areas really have a bridge between them. And one community can learn a lot from another community and vice versa. So this is really exciting thing as for me. And I wanted to stress that there are open questions in this field, like G-2 data versus theory discrepancy, which is not resolved since, say, 10 years, maybe more than 10 years. And there is a very good opportunity for new physics search, namely the search for charge-Lepton flavor violating decays. And I highlighted that there are new experiments which are to start this year or in a couple of years in Japan and the United States at Fermilab and at JPAR. So that's it. Thank you for your attention. Thank you.